Jake? Hello, everyone, and welcome to this first edition of Astronomy on Tap of the Year. I am Laurent Legrand, and I will co-host this edition with Jake, who will present the pub quiz later. For those who are used to our event, we changed a bit the format. So this time we will only have one speaker, which will allow you to ask all the questions you want, and we will be able to ask them all to the speaker. So we try to make a bit more interactive and a bit shorter. So the event is going to go as follows. I will first present a few news very, very briefly about astronomy and space recently. Then we will have the talk by Jason, and then during which you can ask all the questions you want on YouTube and Facebook, Twitter, all our social media. I will then ask all your questions to Jason, and we will then all be able to go to the Zoom pub, during which we will have the pub quiz. The questions will be on the talk, on general astronomy related questions, and also on the news that I'm going to present now. So so listen well. I will now share my screen. So very briefly, the Astro News. So first, this is not really news, this is more historical fact. The 4th of February 1974 was the end of Skylab 4. What was Skylab 4? It was the last mission to go to Skylab with 3 members. So Edward Gibson, Gerald Carr, and William Rogue that you see on the right. And this mission started the 16th of November 1973 and ended the 8th of February 1974. And they were doing a lot of scientific experiment in the area of medical activities, solar observation, Earth resources, and other experiments. Why is it really interesting? It's also because Skylab is actually the first United States space station, and it was launched by NASA in May 1973. And Skylab 4 was the last mission, so it didn't. It stayed it was used for a year, and it was operated by 3 astronaut crews: Skylab 2, 3, and 4. So 4 was the last one. And this station disintegrated in the atmosphere in July 1979 because they were unable to reboost it in a sense. Then the second news is that recently, actually not so recently, between April and May 2019, one program detected strange radio wave emission from Proxima Centauri, so the closest star to our sun. And what's interesting is that the info was leaked to The Guardian in December 2020. So you might have seen the article. But the thing is, there is no paper so far, so we don't know. We haven't been able to find, at least now on the internet, what was the signal. What was it only detected in April and May, and what are the characteristics of the signal, for example. But this had made a lot of noise because recently everything has been around aliens. But the thing to keep in mind is that it's only a candidate. So that's why there has been no paper or anything. It's because although the info has been leaked, there is no conclusive proof. And to stay on this, recently we have heard again about Oumuamua, which you might have heard already about it in 2017, is this strangely shaped interstellar object speeding through the solar system. So it's the first object detected that was from that passed through the solar system that came from outside the solar system. And why do I talk about it now? It's because last month, Abraham Loeb, a researcher at Harvard, published a book on its possible alien origin, which made quite the ruckus in the scientific community. But so far, we have no conclusive proof. All the different characteristics, the speed, the shape, they have been also possibly explained with natural causes. So we don't know. Otherwise, if we would have proven that it's alien, we would have heard about it much more. And finally, the last news is that the first private crew is going to go to the ISS. The commander is a former NASA astronaut now working for Axiom Space, which is the society that is sending them to space. And then you see here that there is some financier, some businessman, an entrepreneur, and they will go to the ISS for 8 days flying on the SpaceX rocket. And so you might think that finally this is coming to us, and maybe you will be the next one to go to the ISS. But of course, as you can guess, it's quite expensive, and so they each have to pay $55 million just to go there. But it's quite exciting, I'm guessing. Now the last news that unfortunately is not it has been removed, sorry, is that on the 11th of February, it's the International Day of Women and Girls in Science, which is extremely important. This has started in 2015 by the United Nations, and this year's theme is to promote the role of women at the front of fighting the COVID-19 pandemic. And so it's very important. And if you want more information, go on the United Nations website. They will have a conference on the 11th with experts from different fields. And it promised to be really exciting. But for now, we have another very exciting talk by Jason Nordhaus on what happens when a star falls onto another star. Yes, Jason.
Thanks, Laurent.
The floor is yours.
All right, let me share my screen here. Okay, so I assume everyone can see these slides. Yeah, so thanks for this invitation. I was telling Laurent and Jake earlier, this is actually, you know, I've spent a lot of time trying to avoid giving Zoom talks during the pandemic, and these guys are very persuasive, and so this is my first Zoom talk. So that's sort of interesting. But I thought what I would discuss with you, with everyone today, is sort of what happens when a star falls into another star. And I won't just talk about stars. I'll also talk about a whole assortment of objects, planets, you know, brown dwarfs, neutron stars, black holes, these sorts of things. So really, what happens when something of some sort of object falls into a star? And I'll just tell you the answer right away. And this picture here on the slide sort of gives you some indication, but oftentimes it blows the star up in spectacular fashion. And so this is a nebula that's sort of associated with a star that has, you know, ceased burning in its core. Potentially something fell into this thing and it exploded. And it didn't just explode sort of in a spherical shape. It exploded in a sort of pattern here, where you see a lot of like material sort of in the northeast, southeast quadrant here. And then if you look really closely, down at the center there, you sort of see some evidence of an S shape. There's like very faint gas, as you can sort of see in this image, and it has a sort of like elongated, stretched S shape to it. And that's usually indicative that something else came into the star and moved things around and spun it up a little bit and caused the star to maybe prematurely explode. And so I'll get into like what that means, but the takeaway, like if you don't take anything else away from this talk, is you should take away the fact that stars do fall into other stars. And when that does happen, it's very energetic. They put a lot of energy into the star they fall into. They put a lot of angular momentum into it, and they often means that the star just will blow up. And I'll talk about what time scales they blow up on. But before we get to that, we should at least talk about the two different channels that stars evolve through their life cycles. And probably a lot of you who are joining for this talk, have seen this sort of thing before and know something about this. But stars can generally be grouped into two classes. Stars that are sort of like low mass, they're like our sun. These are the most stars in the in the galaxy, in the universe, are mostly things like our sun. And they start out, they form in clouds. But what happens is when they stop actually burning hydrogen in their core, their sizes change drastically. And I'll show a graphic in a minute here of what that looks like, so you get a better visual sense. But they become what is called giant stars. And so the radii get really big. And it's at that point typically that if you have another star, or you have a planet, or you have something orbiting around it, that's the time when things typically can fall in to the envelope of the other star. Now, for the low mass stars, when their evolution stops and all their gas is gone and they're left with whatever happens at the end, they leave remnants called white dwarfs, which are these sort of carbon-oxygen inert bodies that are about the size of the Earth. And that's sort of the byproduct of a star like our sun. The massive stars, though, and these are things that typically have masses at least 8 solar masses greater than our sun and upward. These things also go through sort of giant phases where their radii get a lot bigger as the burning in their central regions changes, and they burn different elements. So they get really, really big too. And their fate is a little bit different typically because once they burn up to iron, they can't sustain themselves up against gravitational collapse. And so they collapse it on themselves. And that central region of the star becomes extremely dense and can form a neutron star or black hole. And during that process, the star will violently explode as a supernova. And so the byproduct of really massive stars is two potential things. It can make a neutron star, which is something on this, the size of maybe of a city. And they can also make black holes, which have size scales of maybe like miles. So that's sort of interesting. So here, I'm just showing a plot of like throughout a star's entire lifetime, what does the radius look like? And so the first thing to notice is the label for the x-axis here is gigayears. And so I put over here on the side 10 to the 9, because gigayears is something that you may or may not have heard the term before, but it's essentially a billion years. So a star, and I think this is starts with a mass of around 1.5 solar masses typically. So it's like 50% more massive than our sun. Its lifetime is about 4 billion years or something around there, maybe 5 billion years. But if you look at sort of the left-hand side of this plot, what you see is it forming its life. So it's a cloud that's collapsing down, and this long period in the middle of the graph, and I don't actually see my pointer, so I'm not sure I can highlight this, but you can see like a huge region of this plot, nothing really happens. And it's called the main sequence, and that's where our sun is right now. It's about halfway through the main sequence, so it's halfway through its lifetime. But in this main sequence phase, there's not many changes that are going on. It's true the sun, has a solar wind coming off of it. It's slowly losing some mass. It's doing things like it has like sunspots that will appear periodically, but the structure is not really changing much. It's sort of stable. Not a lot's going on. But as the star gets much older and it starts to basically use up its fuel, the structural changes in the star can become quite dramatic and happen, fairly quickly in evolutionary timescales of the universe. And so if you look over on the right-hand side of this graph, you'll see this label here where I wrote giant stars, and you see the radius spiking. And so the first thing to notice is that this plot is log scale plot. So where you see on the y-axis, you see 2, that means 2 factors of 10, so it means 100. So these stars go from sort of having a radius of about the sun's to suddenly having something that has a radius or a size that's hundreds of times bigger. And so so that's the time again. So if you have a star and it's sort of orbiting around another star, and they don't have to be reasonably close, but if they're sort of close, when this one here gets a lot bigger, it'll just swallow the other one. And now if a star was by itself and sort of just evolved on its own over time, what would happen is it go through two of these big giant phases where it expands a lot and then it'll contract some, and then later it expands a lot again. And then after that phase, it sort of bleeds away all of its mass and its envelope. And what you're left with is just the core of the star, which is the white dwarf. And that's that carbon oxygen degenerate core I was talking about earlier. That is about it's about the size of an Earth. So you have something that goes from like hundreds of times the size of the sun to rapidly contracting down to something that's about the size of the Earth. So there's a lot of different size scales that happen here. And to give you sort of just a little bit better idea about the time scales over which these things happen. So for something like our sun, the first giant phase is called the red giant branch. And that typically has a time scale of 10 to the 7 years. So it's, you know, in the history of the universe, it's fast, but it's an intermediate time scale. It's not super fast. That evolutionary swelling up takes some time. Now, that second giant phase is what's referred to as the asymptotic giant branch, and that's a little bit shorter phase. That's, you know, that's about 100,000 years or a few 100,000 years. So again, in the history of the universe, it's sort of a blink of the eye, but for humans, of course, it's a very long time scale. Now, typically, when you look at these giant stars, if they're by themselves and they look normal and they're just by themselves, they look spherical, and which is what this top right image is here. That's a sort of measuring the light off of an AGB star, and what you're seeing is it's almost completely spherical. If they have objects orbiting them around them, that light can look very asymmetrical, and you can see sort of for some things in the galaxy, for instance, you'll see even systems where like they've got shock waves that are sort of these spiral arms coming off the star, but it doesn't look like a normal spherical distribution. And for the guys that we think sort of eat other objects, you can sort of instantly go from something that looks like a spherical star just hanging out, it's just bigger, to all of a sudden looking like this middle picture here. And in this middle picture, you can see that the symmetry of the system has been like broken, completely broken. You've got sort of still those spherical shells, which are probably mass coming off a star back when it was sort of spherical. But now you can look at and you can see these huge sort of jetted structures that are going in the northeast, southwest sort of direction there. And those are like, I mean, we sometimes call them jets or we call them collimated winds, but they're very fast flowing ejected material from the star that's going like rapidly being accelerated out of the system. And if you look really, really closely in the middle there, you see this sort of darkened area right in the center of those concentric rings. And this is actually an infrared image. So what you're looking at there is you're looking at a lot of dust and things that have blocked the light from that central object there. And there's a big amount of dust, like a donut-shaped dust in the center, and then out the top and the bottom of that disk that you're seeing is where these jetted structures are emerging. So again, the takeaway here is that you go from something completely spherical to something that suddenly blows itself up on a pretty fast time scale of maybe 1,000 years or so. And eventually that material moves away farther away, and you get to see deeper and deeper into that central region where that's really where the interesting stuff is happening. That's really where the star has fallen in. And you can find systems where like not only has something fallen into the star, but it survived the whole process. And what you're left with is that white dwarf here and the other star really, really, really close to the white dwarf. And so in those cases, you know this thing fell into its star. It interrupted that star's evolution much earlier than it would have been if it was by itself, and ejected all this material from the star, and yet survived and emerged the other side in a very tight binary configuration. And so to give you some examples of systems that we think are sort of like that, you can see they've got diverse shapes, diverse processes going on. But the key thing between all of these is that they don't look like spherical stars. I mean, they look like something dramatic has really happened in the system to change the symmetry from something that's a sphere to something that looks like this. Some of these are really interesting too, because if you look at the one, I think all the way over here on the right, you see these little like red blobs sort of outside of it. Those are like very, very high velocity ejecta that have sort of shot through and out the side of the slower moving gas. So you see extreme examples of symmetry breaking. You see gas being accelerated to much higher velocities and the gas having much more energy than it would if it was just a single star. And the source of that, of course, is we think is a second object that's fallen into the star, because it gives a lot of energy and it gives a lot of angular momentum to the gas that otherwise wouldn't be there. Okay. So just to try to give you some sort of sense of this visually, and this is, I made this to about the right scale here, but here's your red giant star. It's red, it's big. And if you had to guess where the sun was in relative to this, the size of the sun relative to this, think about it just for a few seconds in your head. Like, I'm going to put the sun on here, but give yourself a few seconds to think of like what size of this you think the sun actually takes up. Okay, so hopefully everyone has their guesses, and let's see. So there you go. It's this little tiny dot right here. And again, it's something like a factors of a few hundred, like 200 to 300, 400 times smaller than the red giant star, depending on the mass of the star that becomes the giant. But now you've already got a sense of this, right? You've got this something like our sun, and it's plunged into this red giant star. And inside this, there's a lot of stuff that can go on. And actually, before I even talk about that, let me talk a little bit about what happens when the sun goes in here. So it's sort of like, what do I want to say? It's sort of like if you're swimming and you jump off a swimming pool and you plunge into the water, right? You hit the water, you feel it, you immediately go into it very fast, and then you slow down as you sink a little bit deeper into the water. The exact same thing happens with the sun here, except it's an orbit. So you have a big star here, and then the sun comes in and it plows into it, and very rapidly, because it's encountering all this material from the giant star's envelope, it's very, very rapidly losing its own orbital energy and moving down towards the center. So what ends up happening is it just comes in and it orbits, and it very quickly moves towards the center. And I'm going to show you some simulations of this actually a little bit later in the talk. But the reason why it loses that energy is because it's slamming into all this material from the giant star itself. And that's taking energy from the orbit. It's transferring that energy to the gas of the red giant star's envelope. And because it's going from the orbit to the envelope, it means the orbit is actually shrinking rapidly. And so this is the main mechanism we think that the universe uses to make these really, really tight binary pairs. Now, a few slides ago, I had talked about doing this and making white dwarfs and making neutron stars and making black holes. And so this is actually one of the main channels we think for creating tight black hole pairs, or tight neutron star black hole pairs, or neutron star, or white dwarf, or black hole white dwarf, or all different flavors of these things. And why is that sort of interesting? Well, as also probably many of you know, we've detected gravitational waves from the mergers of two black holes and binary neutron stars. And so how you get two black holes close enough to merge, or two neutron stars close enough to merge later through a different decay process in their orbit, gravitational radiation, is this process here. If you look at those stars and how they evolved in time in a binary, and you run a calculation forward in time, you'll have one of them blowing up as a neutron star, the neutron star going into the other star, rapidly getting down to the center, and the other neutron star or black hole being created in that process. So this is a key component of how we make very, very tight tight binaries in the universe that then later can merge and do things like produce gravitational waves. Okay. So to give you a little sense of some of the outcomes here is, it's not always true that the binary will actually survive and come out in a very tight orbit once this process is over. Sometimes what happens is if the object that goes into the star doesn't have enough mass, maybe it's something like a Jupiter planet, Jupiter mass planet, or 5 Jupiter mass planets, or even higher, what ends up happening is it comes in and that orbit doesn't actually have enough energy and angular momentum in it to actually blow the star apart. But it has a lot of energy and angular momentum that it can spin the star up. And so the orbit still shrinks and shrinks and shrinks and shrinks until that planet, or whatever it is, gets close enough to the core of the star. And then the gravity in the core of the star is so strong that it just tears the planet apart. And I'll actually show some simulations of this happening too in a bit, so you'll get a sense of what that looks like. But in that case, what happens is the star survives. You know, it might be rotating fast. It might be sort of sitting there. It might be like a little, squished or something, but it's still roughly spherical. And it's ingested a planet or some object, and it's not blown itself apart. But that thing has torn apart down in the center of the star. It's added a little additional fuel for the star to burn. It can have it can make different elements that bubble up to the top of the star's surface. So there's some sort of things that you would expect to happen in this case. But the key is, in that case, you have a star that's evolution is very different because it ingested this planet or this other body. So it doesn't go its normal route, but yet it still sort of looks like a star. Now that's one case, and that's the bottom panel here. And actually, I'll talk a little bit about this more, because when those planets actually disrupt and tear apart in the center of the star, they make disks. And those disks themselves can do things like make very strong magnetic fields, which then create a white dwarf that's like highly magnetized when the star does finally lose its envelope. So there are consequences of that. The top two panels are more for binaries that survive. So you've got your giant, the thing comes in, it spirals all the way into the center here, and then the envelope blows off. And then you've got the core of the star plus the other star here. So you got the white dwarf and you've got the star here, and they're orbiting very tightly. And when this happens, because the orbit is in one plane, it's like it's in this plane, right? It's not like it's going in all different directions. No, it's like mostly orbiting in one plane. What that means is you're injecting all of that extra energy and momentum into one plane. And so that pushes material predominantly out in one plane. And that's how you get these like donut shapes that we see in a lot of these images. You dump all of your energy in this like plane that looks like this, and you push all the material outward. Now the jets, so we talked before about like you get a disk, you get a torus, but then you can get these jets or these collimated outflows coming out the sides of that sort of those disks. And the way you can do that is there's actually several different ways you can do it. You can create very strong magnetic fields that push material out. You can have very fast material that's slamming into sort of the disk, and it's getting pushed up like this. So it comes in here and goes up like that and goes down like this. There's a lot of different mechanisms, but once you naturally create these sort of disks with a lot of energy in them, then material seems to want to go out the poles because it's easier for it to get out the poles. And I think that's the key sort of takeaway there. Okay, so you could ask the question of like, how do you know when, like, let's say you got two stars here and you got a star here. And these stars are just starting their evolution and they're orbiting around. And I guess I should back up and say also that like most stars, I would say like half the stars probably in the universe form in binaries where there's another star. And then if you think about planets, then maybe it's every single star in the universe probably has something orbiting around it. So maybe not all blow up, but some of them do. And it's not necessarily a small fraction. It's probably actually a large percentage of those. So one of the things you want to answer, or you want to think about, is if you have a star and you have another orbiting body and they've just been born, they're just starting their evolution, orbiting around each other. how do you know like what will happen to that? Like what are the main things that decide whether this one object plunges into the star, or maybe if it doesn't plunge into the star? How do you even get a handle on when that happens, or what, what or the predictive things that help you decide if that happens or not? And there's sort of two physical effects that are sort of competing with each other. The star itself is losing mass. When it becomes a giant, it starts to blow off mass in fairly strong winds on its own. And as it loses mass, that tends to make the binary want to actually get bigger. And so that's helping you avoid plunging in. But at the same time, there's another competing effect, and that is that you've got a big star over here and you've got another object orbiting around it like this. And because this guy's slowly rotating, typically giant stars don't rotate very fast. The orbit tends to be faster than the orbit here, or the rotational period of the giant star itself. And so in that case, the orbit actually wants to decay because there's a tidal bulge that's raised on the star. And it has the opposite sign of the tides for the Earth-Moon system, for instance. So the Earth-Moon system is actually expanding slowly. But that's because the Earth rotates much faster than the moon's orbit. For these giant star systems, it's the opposite. The giant stars are basically, you can think of them as almost not rotating at all. They just sit there, and then you've got the orbit going around. And so in that case, there's a tide that's raised on the star by the orbiting companion, and that makes the orbit actually move towards it. So it makes it more likely that that star will plunge into the other star. So you have two competing effects. You've got the mass loss from the big star that's making the orbit expand, and you've got this tide which is making the orbit shrink. And so you can figure out sort of a critical separation about where like tides win or mass loss wins. And so you can quickly say, like, if you're a circular orbit and you're here, you're going to plunge in, but if you're a little bit farther outside, you're going to push and go out. And what that basically means is that there's at the end of the day, when the system has evolved to make a white dwarf, you've either plunged in and you've either survived that interaction in your really tight orbit, or you've been pushed all the way out that you're now far away from the sun. But really, there shouldn't be a lot of stuff in between that. And I'll talk about that in a minute here. So showing that a little bit more here graphically, let's say that here's your star all the way on the left, your main sequence star there, and you've got the same, you can call it another star if you want. You've got the blue star and you've got the red star. So the blue star is a little bit exterior to the red star, and what ends up happening is that one, the winds from the main star win, and the orbit moves outward and the orbit expands, and it avoids plunging into the star and it just gets pushed farther out. The red star, on the other hand, is a little bit interior to that, and its fate's different. The winds off the star don't win out. The tides do. The orbit decays very quickly and it plunges right into the star. And then that orbit rapidly shrinks down to the point that it either survives that and it is a very tight orbit around the white dwarf, or it doesn't and it's just gone. And so all the way on the right side of this, you see this what's labeled the gap. This is the region around a white dwarf, where you should really not expect to find anything. And if you find something there, it's really, really interesting. So to show this another way, and I'm just putting this up because I'm going to add a point to it in a second. Really, this is what's allowed by, I would say, theory. Anything sort of in this pink magenta-ish area is okay. Like this stuff could have formed through plunging into the star or merging on the other side. And so this is at the time, I wrote this paper. These were all of the known white dwarfs that had very close companions with very well measured orbits around them. And what you can see is they're all sort of in this like magenta region over here on the right side of the plot. Now the greenish sort of regions are where theory says there should be nothing there. And as of the time I wrote this paper, there was nothing there. But recently, actually 2 months ago, someone found something where this yellow dot is that they just put here. And so this was a paper in a very high profile journal, Nature. And the conclusion of that paper is the way it got here is not through this channel of plunging into a star, but there's a third body farther out in the system, and there's a mechanism for when you have 3 or more bodies to scatter the object down closer to the white dwarf. And so the consensus, I think, at the moment is that this one probably got pushed all the way down to where it is because there's some other further out triple star in the system. So that was sort of, I mean, that was sort of exciting and very interesting. And this was breaking news. This is a few months ago. This paper came out. Okay. These are some of the same plots that I just shown. They're just in a slightly different form. And when you think about when a star plunges into another star, you can sort of do your what's called back of the envelope calculations, where you can sort of predict where that plunging in part stops and how separated it is from the white dwarf. And the gray points in the back, the sort of the gray scale, this smudged out area, this is what most people predict for white dwarfs. They actually say that there should be a lot of things around white dwarfs, and they should go out, anywhere from a 1/10 of a day period all the way out to a 100-day period. And if you actually just plot the systems that are known, what you see is that they all pile up at about a day period and less. So the orbital period's a day, or it's shorter than that. There's very few that have longer periods than a day, and there's certainly not things that are out at hundreds of days. And this is not a selection effect. You would see them if they're there, but theory just gets it wrong compared to the observations. And so that's a great thing so I'm a theorist, so I like to think about places where you make a prediction, it doesn't match observations because it means something else is going on there. And so, I've written a set of papers with a graduate student of mine over the last couple of years, where we looked at what physical effects are missing from the theory that would lead you to basically have an interaction where the periods become very short, less than a day. And what I haven't mentioned yet about giant stars are they are very what's called convective or turbulent. They're like giant spheres of boiling pots of water. And almost the entire star is a very turbulent mix of gas that's just bubbling up to the surface. And so literally thinking about it as a giant boiling pot of water is actually pretty good. Why is that important? Well, it's important because convection has some very nice properties associated with it. The first of which is it can transport energy. And so remember I was saying that as you plunge into the star, that orbit is putting energy into the gas so that the star can blow itself up and be pushed out. And the reason here you're seeing sort of a lot of objects at 100-day periods, 50-day periods, is because there's plenty of energy in the orbit to just push that out material and stop there. Yet that's not what happens in nature. That's not what happens in the universe. So this already points to the fact that this phase where a star plunges into another star actually has to be pretty inefficient. If it was totally efficient, you would see these things at very long periods, but we don't actually see those. Now, how can it be inefficient? Convection can help you here, because what convection does is, as you move through the star, it's bubbling and bubbling, and it's bubbling all the way up to the surface of the star. So we can take the energy in the gas and it can get it up to the surface of the star, and then that energy can leave via light, via photons. So it radiates away, and the energy can leave the star without the gas actually leaving the star. And so it's cooling. It's cooling exactly like your boiling pot of water does. You see the boiling pot of water going on. You see some steam coming off, there's some gas coming off, but there's heat coming off the surface. And it just keeps bubbling because you've got some heat source you've got fire, you've got whatever's going on in your stove there. So it's sort of in a steady state like that. The same things happens in these stars. As the one plunges in there, it gives more energy to the star, but those turbulent little bubbles, just like your pot of water, they rise all the way to the surface of the star, and then they cool through releasing light. And so they cool and they fall back down. And so for a large region of these stars, convection is totally fine. It can transport all of that energy that the other star is giving it to the surface and push it away. Convection is also nice too, is it mixes the gas very efficiently. And you know, if you pour in a bunch of pasta into a boiling pot of water, yeah, you want to stir it a little bit initially, but sort of it just bounces around and some stuff might stick together, but for the most part, it would be fine even if you probably didn't stir it. And so what you can do is you can compare how fast the orbit shrinks to how long it takes the convection to transport the energy to the surface. And if the time for the convection to transport the energy to the surface is very short compared to how long it takes the orbit to decay, that means that convection is fine. It just takes the stuff to the surface, to the surface, to the surface. It doesn't actually work to blow the star up at all until that time scale switches. And then suddenly, if the orbit decays too fast, convection can't get rid of that energy, and that's when the star would explode. So if you do that with these things, and you look at the right-hand graph here, what you're seeing is that basically in this case, anytime one of these lines here crosses the blue line, that means it's blown up the star and it's survived in a tight period orbit. But what you can immediately see is like this should mostly happen at periods that are less than a day. And that actually matches observations extraordinarily well. And so this is the first paper. We did this with one of my PhD students, Emily Wilson, in 2019. And we followed this up and we actually looked at another class of objects, which are double white dwarfs in short period orbits. These things could be future gravitational wave sources with space-based gravitational wave observatories such as LISA. But they also can make type 1a supernovae potentially. So these are interesting objects anyway because they're progenitors of those sort of events. But theory and observations also don't match here at all either, how you form these things. And so we said, okay, we've got convection in these stars. Let's apply this to the phase where they make double white dwarfs and see how well we match the observations. And each of the green points here is an observed double white dwarf system. And the gray background is what we would predict from our theory. And this is like a pretty good match. I mean, it's not 100% perfect, but it is like way better than anyone has been able to do, I think, up to this point. And so we published this last year, 6 months ago, something like that. So I would say that like for this phase where a star falls into another star, convection and that transport of energy to the surface and the radiation of the energy away is extremely important for understanding the physics of these systems. Okay, now I said I was a theorist. I said I would show you guys some simulations. I will do that now. So one of the things theorists can do in their toolkits is they can use really, really big computers to run simulations of various things in the universe to help them understand complicated systems. And so I'm part of a group that does this. We have a lot of students that run these types of simulations. We publish this work, and so I'm going to show some of that, share some of that with you guys now. What I want to do first, though, is sort of give you an introduction to the type of tool we use. So we use what are like sort of distributed computing software packages that use a lot of cores, a lot of computer cores, thousands, tens of thousands of computer cores all working at the same time to solve the physics. And you typically do that on a grid, a numerical grid. And I'm going to play this movie here. And this is what we called an adaptive mesh refinement code. And so you can see as you look down at the center here, the resolution is getting much, much better compared to the outside. And that's because this type of code can dynamically like allocate resolution based on where there's interesting physics happening. So it's a sort of a smart code in that it can do it in real time as the code's running. So places where you've got like gas, swirling around really fast and you need to get the right answer there, it puts a lot of cells there, little fine cells, so you get a very, very sharp image. Whereas out, somewhere else where you don't need, where things aren't moving a lot, you put a few cells there because you don't really care, because it's not such a big deal. So that technique is called adaptive mesh refinement, and this is one of the main tools we use. And now I'm going to show you actually a simulation of a star falling into another star. So before I sort of have the one star fixed, and then the companion comes in and it moves around like this, and then it hits the corner, and the core and the star get very close together. It's going to be a slightly different frame of reference here. The camera is actually fixed on the star that plunges in. So it looks like the star itself is going to be like sort of moving like this. And we actually keep it lined up so that the main star is always in the same place. So it's not going to really look like a big star with something swirling in the middle. It's going to look like the thing that's swirling is fixed and the other star is moving relative to it. Now, what you'll see is on the left side, you'll see the core of the star come in, and that's the thing that's going to form the white dwarf. And it's going to be the bright spot, and it's going to get closer and closer to the other star. The other star you're not going to initially see because it looks like it's black, but once the gas moves around it, you'll see it very clearly. Now, notice the time scale here. I guess I hadn't mentioned this yet, but how fast this whole process is of a star falling into another star is on the order of years to tens of years. So it's pretty fast. That whole thing is over very fast. And so we only simulate, I mean, you can see it, you can measure it here in days. We're not even simulating a full year. This one is actually particularly fast. So I'm going to start this now. Okay, and all that gas swirling around the center there, that's it interacting with the companion. The bright spot on the left is the core of the star. Now you can see both of them very clearly. And if you keep watching it, it's getting closer and closer and closer. And so this whole thing takes place on the order of like 40-ish days. So a little bit more than a month. And you can follow this longer and longer and longer, and they'll just keep getting closer and closer and closer together until they stop. This takes up a lot of computational resources. So typically, like, you could simulate for a few months, but that's typically all you can do, because these large computers use a lot of electricity. You don't get unlimited resources. You have to share them with other researchers. So you can't follow this indefinitely. But so this is something that's starting. The star is swollen up to about where the Earth orbits. The other star plunges in, and then you can see them like getting closer and closer together as time goes on. And you can also see these like spiral patterns coming off it. It looks like a sort of Archimedean spiral, and that's indicative of when these two binaries get close together, you'll get sort of shock waves coming off in spiral patterns. So that's another observational thing, that if you see that, it's an indication that there's a hidden binary down in the center. This is going to be sort of the same thing, except now we're looking at two angles. One, you're looking at it edge on, so you'll see the disk form. And you'll see like the concentration of stuff in the orbital plane. It's going like this. The other is face on, where you rotate the camera, so now you're looking at it more like this, and the orbital plane looks like this. So you'll see both of those side by side. The green circles show you the locations of the white dwarf core and then the other star that's plunging in. And this gives you a little bit better view of what the larger symmetry, or larger scale stuff in the problem looks like. Now, if you were to compare this sort of thing with those images I had shown you earlier, those beautiful Hubble Space Telescope images of these huge nebula, I mean, those things are factors of like 10,000 larger. So this is what's happening way down in the core of that system. And as the gas travels out and out and out, eventually you'd see, you'd hope it would have some sort of shape like those images have. But we can, with the computers, you can only study it in finite regions. And then with the observations, you can only see on the large scale. It's harder to see down into the central portions where all the interesting stuff like this is happening. Okay. And now let's see, how am I doing for time? Okay. I probably only have like 5 more minutes of material here, but I'd also mentioned that planets can plunge into stars too. So it's not just other stars. It's really any close object. And planets can certainly plunge in. So in our own solar system, the sun will expand out to about where the Earth is. The Earth will go in, Mercury, Venus will go in. Mars is sort of on the border. Jupiter will actually avoid, Jupiter will be able to avoid it, I think, and move outward. It'll expand a little bit. But back in 2013, with a colleague of mine, Dave Spiegel, we looked at sort of given what was known about the exoplanets at the time. So any star with a measured planet around it, we calculated out sort of the fates of those systems as the stars evolved forward to try to figure out like what's the minimum mass planet that would be able to blow up the star and survive, and also to say like how close can a planet be orbiting before it would fall into its host star. And so if every dot on here is a planet that was at least Jupiter's mass around a star that at least had a solar mass at the time. And we ordered them all by how close they were to their parent stars. And if it was a red dot, what ended up happening is that planet would plunge into its star on the giant branch. And it would, if it's a red dot, it would not survive the interaction. It would travel deep into the star and it get torn apart by the gravity of the core of the star. And I'll show simulations of that in a minute. But what you can see here is like the closest object that actually, so first of all, you see that no objects survive. All of these planets that were known at the time would not actually survive the interaction and blow off the star. They would all go in and they all get torn apart. The green dots and the blue dots here are planets that would actually be able to avoid plunging in, and their orbits would move because their stars were losing mass and they were just outside that critical radius or critical separation where they'd avoid it and they'd move outward. And so, at the end of the day, when you'd have a white dwarf and you'd have a planet, you look to see where like that closest green dot is, and it's something about 8 AU. So 8 times the Earth's orbit is basically where you would end up. And so like if you wanted to avoid it, you'd have to probably be at least 5 or 6 times the Earth's orbit, and then you're right on the edge and you're probably safe, and you can move outward. Now, when I say safe, I don't really mean safe, because when these stars get huge, they put a lot of radiation on the planet. It would be terrible. I mean, the temperature changes. You probably move outside your habitable zone if you were in one. Like chaos ensues. Planet probably is not inhabitable at that point. Jupiter is the purple star, and so Jupiter moves from its current location out to about 10 times the Earth's orbit, but it would avoid it. And now I should also say one caveat here is that these are where you assume that there's just the star and the planet orbiting. If you have a lot of planets orbiting, the dynamics can do weird things, and you can get scattering, and you can get things being flung into the star or flung out. So this calculation is just true for things where you only have that one planet and the star itself, and it gets modified if you have lots of other objects in the system. Okay. So the planets, though, that don't survive. So if you threw Jupiter into our sun, for instance, it would move its way down to the center until it gets to the part where that gravity from the sun's core is so strong that it actually overcomes the planet's own gravity and it tears it apart. And it just tears it apart into a bunch of gas and debris and things that just rotate around and smooth out. And they could actually make a disk inside the star. And that disk inside the star is actually around that core. And so that material, that gas around the core there, can then work its way down and become part of the white dwarf. And they can do different things in there. In astrophysics, this is called actually an accretion disk. And these are very different accretion disks than you typically see in astrophysics. The disk itself is very cold because it's made from a planet. So it's just its planet's temperature, which would maybe be 1,000 K, something like that. But it's at the center of a star, which is like 10 to the 7 K. So you've got a very cold disk in this super hot environment that's just being baked. And these disks have interesting properties that they can actually make very strong magnetic fields that could attach themselves to the white dwarfs. So strong, in fact, that they would emerge out, and there's a whole class of white dwarfs that have super strong magnetic fields. It's like 10% of white dwarfs. And so we proposed this as a mechanism for creating these highly magnetized white dwarfs a decade ago, basically. And so we've done some simulations of this since then. And this is my last slide, and then I'll stop. But what you're going to see actually here is you're going to see the planet being torn apart by the gravity of that core. And so this one on the left side here, the top left, shows that the center region of that is the core of the star. The planet is this blob with this arrow on it. It's going to be rotating around this way, and you're going to see it torn apart. The image or the movie to the right is going to show this for another planet. And then the bottom is going to show you a later stage when there's the disk is present from the disrupted planet and how that disk evolves in time. And so this is another series of papers with another one of my graduate students that we've published. So we start all these so you guys can see how it goes. So you see the planet just being like totally destroyed, and you see this sort of disk forming down in the center. You also see a tail of material from the back edge of the planet that just sort of, it'll move outward, and then at later times it'll come back in. And so that's all planetary debris just being torn apart inside this super hot star. And what's sort of interesting here is the disks actually last quite some time. They don't instantly go away. It takes thousands of rotation times before the disks would sort of merge with the rest of the star. And so that's plenty enough time to do things like generate a very strong magnetic field and sort of have some of that material maybe attach itself to the white dwarf. So again, these are computations using large supercomputers and in investigating the very, very interiors of stars where we can't see what's going on. So theory is a pretty good tool to try to think about the consequences of what happens when a star falls into another star. So I think I'm happy to stop there and hang out with you guys and take whatever questions you have.
Hey, Jason. Thank you for this very interesting talk. Advanced topic. The simulations are really amazing to look at.
Thank you.
So yeah, they're using gigantic computers, as you said. So yeah, we have a few questions. So on the beginning of the talk first, what are the type of stars that live the longest? And also on that, what is the known star that has had the longest lifespan? So I'm guessing what is the oldest star we know?
Yeah, okay, so that's a great question. So typically, like the less mass a star has, the longer it can live. I sort of make the analogy with, when I teach like an intro astro course, I make the analogy with cars. Like if you have a gas guzzling SUV that just, uses up its tank of gas very quickly, that's a massive star. Massive stars have very short lifetimes. They burn all their fuel and they explode and they're done. If you have a Tesla or some electric car, it can use less energy. It lives a much longer lifetime, and so something like our star, our sun will live. It's about halfway through its life at 5 billion years. It'll live to probably be 10 billion years old. There are a whole number of stars in the galaxy that are less massive than our sun. That not a single one of them has died yet. These things were probably they were born when they were born, and they've never died out. And those are typically like 0.8 solar masses. Below that, they've not had enough time, even in the entire galaxy's lifetime, to evolve to the point where they would die. So about 0.8 is where, like, if you're above that in mass, you may have been able to die, but maybe not. But as you go higher and higher in mass to 5 solar masses, 10 solar masses, 20, then you have very short lifetimes and you're dying very rapidly.
So yeah, the lower the mass, the longer the lifetime.
Yep.
So you answered the second one, which was a scared question. I'm guessing, when is our sun going to die?
Right. Yes. Yeah. So that was a long time away. It won't matter for any of us.
Yeah. And so it will grow, as you said.
Yeah, it'll grow. So our sun, in about 5 billion years or so, it'll start on the red giant branch, and our sun, actually, the red giant branch will be probably a little bit bigger than that later, the asymptotic giant branch phase. But in about 5 billion years, it'll swell up to about where the Earth orbits, and then it'll sit there for 10 million years or so, and then it'll contract a bit by maybe a factor of 10 to 50. It's still bigger, but it'll contract, and then eventually it'll swell back up again. and it'll stay there for about 10,000 years. And at that last 10,000 years is when all the material is just going out into space. And after that, what's left is just the core of the sun, which will be a white dwarf, and all that gas will go out there. And we'll, if you were outside of our solar system and you had a camera, we might make one of these nice, beautiful images. But obviously, if you're, in the solar system, it's not so good.
It's gonna be harder to make the
Yep.
to see it. Yeah, and hopefully, like you say, it's in a long time.
Yep.
What are gravitational waves?
Okay. So yeah, this is a great question too. So if you get to really, really massive, dense things, and you typically need things like these, what are called compact objects. So you either need white dwarfs, neutron stars, or black holes, but you need a lot of mass. And if you have two of them orbiting around each other, you have to deform that mass somewhat. So it has to break symmetry from a sphere and become distorted. And when you do that, it creates ripples in space-time, which are not, it's not light. I mean, traditionally astronomy has looked at light to learn everything about the cosmos. But in 2015, we saw for the first time what are called gravitational waves. And these are sort of like, I mean, you can think of them as ripples in space-time that propagate from an area where you've got two merging black holes. They make a big bang, and you get these ripples that propagate out into space, and they arrive at the Earth. And we have detectors on here, LIGO, that sort of have these huge laser beams, and they have angles. And what they do is they measure the distances between objects. And when one of these waves passes the Earth, these tiny little distances shift, and they can record the wave as it passes by the Earth. And you can link it back. I mean, the goal is to link it to a particular area in space where it emanated from. But even if you can't do that, you know the shape of it. And so you can, there's a whole group, whole groups that study sort of, in RIT, we have, one of the groups in the world that studies this. What happens when two black holes merge? What are those particular gravitational wave signals that propagate out? And in fact, we use that information to say, okay, LIGO saw gravitational wave hit the Earth, and guess what? We can link it back to, it's a black hole of 50 solar masses and a black hole of 60 solar masses, and they merged in this fashion. And you can use that to infer properties of these systems that you would never, ever be able to see with light. Otherwise. And so it's a totally different channel from what light brings us. And these gravitational waves, they can propagate through the center of the galaxy. They can propagate from areas that you can't see with light. So it gives us another window onto the universe in which we can use to study it.
And it's a recent discovery. You said 2015?
2015, yep.
Wow. So yeah, following the question you also answered, maybe you want to develop on that. How long does it take for the smaller star to lose its velocity when it plunges into the large stars? Is it the large star? Sorry, is it days, weeks, or years?
Yeah, it depends on what the thing is, but I would say it's on the order of years. Sometimes it can be tens of years, and in some cases it's even hundreds of years. But typically, if it's the more mass it has, the shorter that scale tends to be. So if it could also be typically years or even sub-years sometimes. But years is sort of the number I carry around in my head.
And now last question, which I think is very, very interesting. How likely is it that we will observe this directly?
Yeah, so this is a great question. That's a great question. Whoever asked that one, it's very unlikely. So in our galaxy, there's about one of these going on at any given time. But then you have all the stars in the galaxy, and so if this star is on the other side of the galactic center, you have no hope to see it. So you have to get really lucky to do it. There have been some claims that's been seen. Some high-profile claims has turned out not to be true. But you can only see it in our galaxy, and there's only one star. So it's sort of like hunting for that needle in that huge haystack. So it seems unlikely that we're going to be able to see it without getting really, really, really lucky, which is okay. I mean, we have enough info about what comes out the other side that you can infer things about how the interaction goes. Obviously, seeing it as it's occurring would be amazing and yield a lot of insight, but it's very difficult to see.
But still, you would like to see it.
Yes, I would love to see it.
Okay. Well, thank you very much. and I hope you'll join the pub quiz, and then everybody will see you at the Zoom pub as well.
Perfect. Sounds good.
Just before giving the word to Jake for the pub quiz, we have just also a quick question on the news that I presented. Do the private crew going to the ISS needs a lot of training? And so I'm not an expert on all this news. I just quickly check them, but they do need training. One is a pilot, and then they have training as also astronauts, and also one might do science, as I read. We can talk about it more in the Zoom pub, so don't hesitate to join us just after. Now Jake is gonna take over, and you're gonna see the link to join the Zoom pub, sorry, for the pub quiz. So see you soon.
Hi, everyone. Thanks for watching today and joining us. As Laurent said, we will be soon going over to the Zoom pub for the quiz. We'll be running the quiz in the Zoom pub again. We tried this last time, seemed to work well. And so the live stream on YouTube will end and the stream will stop into the Zoom pub, but I will come into the Zoom pub and the pub quiz will be running there. So if you want to take part in the quiz, please go ahead and join the Zoom pub now. It's http://stem.ooo/ZoomPub. Again, that's STEM.ooo/ZoomPub, as you can see on the screen right now in the stream, in the description also of the event. So I hope to see you over there, and then we'll have the quiz, and then we'll be talking to Jason afterwards. So this very shortly will be the end of the stream, and then see you in a few moments in the pub. If you're watching this recorded, then join us live next time, pretty much the first Monday of every month, and then you can participate live online in the pub quiz and watch the talk either on YouTube, or also we show the talk in the Zoom pub. So see you in a minute there. Goodbye, and thanks for watching today. If you haven't already, subscribe.